Sure.
Yeah.
Okay, great. So welcome everyone. Thanks for coming to this yet another seminar of this ESC Talks. Today we have the pleasure of having with us Dr. Sebastian Trujillo Gomez. Sebastian is an expert in theory of galaxy formation, and he works at different levels with cosmological simulations in comparison with observational data. And he also used semi-analytic models through his career. So Sebastian did his PhD in New Mexico State University with Anatoly Klipin. He then moved to Zurich to work with George Lake for a postdoc for a few years. And now he's in Heidelberg. He's also doing a postdoc since 3 or 4 years in the group of Diederik Kruisen. I hope I pronounce it correctly. He told me he's job hunting for next year. So if any of you is interested in his research, I think I said mostly everything that I had to, and let's see what he's gonna tell us today. I think he's gonna talk about a recent work that is put in archive that is of common interest for many of us at the Institute. So.
Thank you. Thank you, Ariana, and thanks also to the organizers for inviting me and making this possible. I hope you can see my slides. I'm very happy to be visiting Tenerife, even if it's virtually, and I hope sometime in the future I can actually be there. So the common thread in this talk is going to be touching on different topics, but the common thread for all these topics is how a better understanding of how galaxies influence the formation of their stars and their clusters and their globular clusters can lead us to a better understanding of the ways that of the assembly of galaxies through observations. So in the background here, you can see a video of a simulation where we follow self-consistently for the first time the assembly of a galaxy like the Milky Way in its cosmological context, along with its star cluster populations. And so those colored dots are globular clusters that are colored by metallicity. And you'll see this is going to come up in the talk in a minute. So like I said, I'm going to talk about three main works, three ways of winding back the cosmic clock. In the first one, I'm going to be talking about how to reconstruct the assembly history of the Milky Way using the globular cluster kinematics that have been measured recently by Gaia. In the second one, I'll go a little bit further away from the Milky Way and into the local universe, and I'll discuss this new class of objects, ultra-diffuse galaxies that have been getting so much attention recently, and why they're so good at forming globular clusters. And in the third one, I will tie into that second point and discuss how globular cluster feedback influences galaxy formation and how it can lead to the formation of UDGs. So let's get started here in our home galaxy. Of course, the question of how the Milky Way formed is central to most of astrophysics. This is one of the big questions. It has a long history, but the advances started sort of in the 1960s and 70s with these famous works, one of them by Egan, Lindenbell, and Sandage in '62, where they looked at the orbits of the stars, of 200 stars around the sun, as a function of their ages. They realized that younger and older stars have very different orbits. Older stars have larger orbital eccentricities, lower angular momentum, and they also have larger vertical velocities, meaning that they're kinematically hotter than younger stars. And this led Egan, Lindenbell, and Sandage to conclude that this is consistent with watching the collapse of the Milky Way happening or tracing it archaeologically using the orbits of the stars. And this requires that the older stars formed out of gas that was falling in radially and collapsing onto the disk of the Milky Way. And this explains why they're kinematically hotter. So you can see just from the power that looking at the kinematics of the stars has for understanding the assembly of the galaxy. A few years later, using globular clusters, Sorensen did something similar. They looked at a proxy for the ages and metallicities, but this time they split the globular clusters into galactocentric radii bins, going from the inner clusters to the outer clusters out in the halo. And they found something very peculiar, that the inner clusters have a very small age spread, whereas the outer clusters in the halo have a large age spread, including young and old clusters. So the inner clusters all seem to be coeval, whereas the outer clusters form at different times. And so they conclude from this that the collapse of the Milky Way might be ongoing. And so they conclude that this is consistent with the outer clusters originating in protogalactic fragments, clouds of gas that are forming stars and clusters as they're falling into the Milky Way. And this is pre-lambda CDM. Now with the cosmological model in place and the initial conditions, we understand that this is a consequence of the hierarchical assembly of galaxies. This is simply the accretion, the formation, the growth by accretion of galaxies, including the Milky Way. And so after the Gaia revolution a couple of years ago with DR2 and all the studies that were able to reconstruct details of the assembly history and in particular progenitors of the Milky Way, we asked ourselves these questions. If globular clusters are the result of regular cluster formation at high redshift, what can we predict for their kinematics at the present day? And does that agree with the Milky Way? And in this way, we can falsify this hypothesis that they're the product of normal star formation. And second, what is the best observable of the galaxy assembly process? What globular cluster property, for example? And third, how do globular clusters compare to stars as tracers of galaxy formation? As you know, most of the work using Gaia has been focused on stellar debris from progenitors of the Milky Way, but we believe that globular clusters are a good complement to these studies, and I'll show you why in the following few minutes. So this is schematically what we're trying to do. This is the problem. In simulations, we have it relatively easy. We have the initial conditions from lambda CDM. We have all the physics. And then we get the evolution of the galaxy, which is represented here by the merger tree, down to redshift 0. At redshift 0, we can look at in exquisite detail at the properties of the galaxies that we form in the simulations. For example, here, the kinematics of the stars and the globular clusters. And you can see how rich this information is. And in the simulation, it's almost trivial to relate it to the assembly history. However, what we want to do is really take the observation. So here's the Gaia kinematics for all the Milky Way globular clusters from Gaia. And we want to relate these back. We want to do the opposite. We want to reconstruct the assembly history of the galaxy from this data. And this is actually much more difficult. And for this, fortunately, we have the simulations, and I'll show you how we can do this. So, but first of all, I want to convince you that globular clusters are actually quite special tracers of galaxy assembly. The first reason is that they're brighter than stars, so they're much easier for observers to study at larger distances. Second, their phase mixing time is much longer than for satellite galaxies, so they stick around for longer, and so they're able to trace earlier mergers. And last, and I think most importantly, dwarf galaxies have more globulars per unit stellar mass than more massive galaxies. And you can see this here. This is the globular cluster system halo mass relation expressed in terms of a ratio. You can see the ratio is constant along decades in galaxy mass, showing that galaxies, dark matter halos, have a constant fraction of their mass in globulars. And if I show you the stars, they would go down here. This is the stellar mass halo mass relation. And as we know, it drops precipitously towards lower masses. So you begin to lose the stars much more quickly than the globulars, and therefore the globulars are able to trace lower mass mergers, at least in principle. But of course, first we need to understand how globular clusters form and evolve. And this has been a matter of debate for the last several decades. It's a difficult problem. It's a difficult problem to simulate in the context of galaxy formation, but we're lucky to have this tool. And this tool is the E-MOSAIC simulations, which were completed recently. And the idea behind the simulations is to be able to self-consistently model the formation of galaxies and their globular clusters in a cosmological context, in a cosmological box, as you can see here on the right, where we can zoom in on, for example, the 25 Milky Way mass galaxies in this box and follow all the way from their large-scale environment down to the galaxy and the details of its populations of stars and clusters, and also go back in time and watch the formation of the galaxy. And the key thing is that it uses the Eagle galaxy formation model, which has been proven to reproduce many galaxy properties. So we know that their galaxies are consistent with observations. And then on top of that, it uses a subgrid prescription because modeling this directly would be prohibitively expensive. We have compared the cluster population, the young cluster populations in the simulations, and they seem to agree with what we observe in the local universe. And additionally, many globular cluster observables, like the high mass end of the mass function, the metallicity distribution, the radial profiles, and many others, agree with observations. So we're quite confident that the model is forming clusters in sort of as a way similar to what the real universe does. And this is key to using them to trace the assembly histories of real galaxies, of course. And the main philosophy of the simulations, like I said before, we have 25 Milky Way mass halos that are selected randomly only by halo mass so that we can sample the full range of environments and assembly histories. And you can see how different two Milky Way mass galaxies can be here in their merger tree. The one on the left has a very quiescent merger history dominated by in situ growth, whereas the one on the right is dominated by mergers. We don't know which one the Milky Way is, although we have evidence from other probes. So and interestingly, we find that variations in the globular cluster systems also reflect these variations in the assembly histories, which is key to be able to relate the two, to be able to connect the two. And so in the first part of this project, we looked at comparing the overall properties of the globular cluster systems across the 25 simulations. So in these diagrams, I'm showing you the velocity and velocity dispersion components in 3D across each simulation. So each gray line, and the median and dispersion are the black line and the shaded region, and also the Milky Way is in blue. And the first thing that you can notice, if you just focus on the simulations, is that typical globular cluster systems co-rotate with the stellar disk. And this is not unexpected if you assume that a fraction of the globulars formed in the stellar disk, as the older works pointed out for both the clusters and the stars. And also, if you look at the comparison with the Milky Way seems to be kind of at the edge. So it has a globular cluster system that is more rotationally supported than average within the inner galaxy. And this is going to be key because this, as you will see later, it points to the Milky Way having a very quiescent late merger history. We can also do more in-depth comparisons. And for this, it's useful to split the populations into metal-rich and metal-poor clusters, because metal-rich and metal-poor probe different progenitor masses through the mass-metallicity relation of galaxies. So here I'm showing you, we can focus on the comparison of the velocities and the velocity dispersions of the metal-rich and metal-poor populations. So taking the difference and the ratio in the case of the dispersions. And you can see that the simulations, which is the color band, shows quite a broad distribution, which is good because it means that we can relate this to the assembly history. And once we compare it to the Milky Way, which is the vertical band, the Milky Way seems to be quite not typical, quite special. The Milky Way metal-rich clusters seem to be more rotationally supported and dynamically colder than the average simulation. And again, this points to them to the quiet late merger history, not disturbing kinematically the in situ clusters. So, but now we want to get to the assembly history of these galaxies. We want to put together a method that relates quantitatively the kinematics of the clusters to the assembly of the galaxies. And for this, we use the kinematics and the merger trees in the simulations to search for any tracers of the assembly of these galaxies, sort of agnostically, just blindly. And so we put together the list of as many kinematics tracers as possible, including those typically used in the literature, the moments of the velocities, orbits, and the integrals of motion. And we split the sample into subpopulations in metallicity and in galactocentric radius. So that gives us a total of 47 kinematic tracers. And then we describe the galaxy assembly tree. We condense it into 32 metrics, including the global redshift zero properties, the growth timescales of the halo and the galaxy, the fraction of in situ versus ex situ growth, the merger timescales, and the merger ratios. And of course, there's much more information than this, but we had to limit it to some degree in this method. And so and then we look for, we search the entire grid for significant rank order correlations, because we don't know a priori what the functional form of these are. And then we model each correlation between a tracer as the independent variable and a metric and an assembly metric as the dependent variable, using a linear model for simplicity. And so here I'm going to show you a couple of examples. We found many, but I don't have time to get into all of them. So for example, we see that a larger fraction of accreted stars produces a larger spread in the apocenters of the metal-rich population. And this is this fit that you see here. And I'm also showing you the prediction for the Milky Way based on the Gaia kinematics. And this is because more mergers, which come from distinct trajectories as they fall into the Milky Way, will contribute to a larger diversity in the orbits. And just from looking at the prediction for the Milky Way, you can see that it has narrow spread in the apocenters of the metal-rich clusters, which means that it has a relatively low fraction of ex situ components. We also find that the redshift of the last merger correlates with the ratio of the eccentricities of the metal-rich and the metal-poor components, and in the sense that an earlier last major merger gives you a lower eccentricity of the metal-rich component compared to the metal-poor. And this is because dynamical heating of the in situ clusters occurs after the last major merger. And so the longer ago this happened will leave a signature on this ratio of the eccentricities. And so from this, we can obtain the redshift of the last major merger of the Milky Way, which is about 3. And so, of course, we find many more. We find that using only 7 kinematic tracers, we can describe 18 properties of the assembly of the Milky Way. And we check this against other independent constraints from other methods, mostly from the stars. And the predictions seem to be in pretty good agreement with the existing constraints. So we're quite excited about this. And so this gives us sort of an overall picture of the assembly of the galaxy that is quite different from what we get from studying the stellar debris from individual progenitors, which gives us a lot of details on one accretion event. This gives us sort of the overall picture of how the Milky Way formed. And so it consists of an epoch of fast rapid growth at high redshift, the redshift greater than 2, where both the dark matter halo, the stellar mass, and the main progenitor grew more rapidly than the median galaxy. It had more mergers than typical, and it had the last major merger quite early at redshift 3, which is much earlier than the median galaxy. This was followed by a quiet merger history at redshift less than 2, with only about 6 mergers, and the last merger happening more than 5 gig years ago, which is also quite early, and this likely corresponds to Sagittarius. We can also get constraints on the merger demographics about a normal number of overall mergers, relatively few major mergers, so again, a quiet merger history in that sense, and relatively low fractions of accreted stars and globular clusters. So you can see this kind of gives you an overall picture of how special the Milky Way is compared to other L-star galaxies. And of course, this is going to have important consequences for the formation of the disk and for the formation of the sun and the solar system. So to conclude, we find that the kinematics of globular cluster populations probe the assembly history of galaxies much more than we expected. There's a lot of information in there, and this relates to the effect of dynamical processes and the evolution of the distinct orbits of things that are accreted from other galaxies versus things that form in situ in the disk. And these are traced by the kinematics of the different subpopulations. And of course, you might be wondering, of course, can we do this with other galaxies? And the answer is yes. We can go beyond the Milky Way. Of course, we have the limitations on the precision of the kinematics and also the fact that we only see projected velocities and positions. So we did some preliminary experiments projecting our galaxies as if we were external observers, and we find that we still recover at least some of the galaxy assembly features during this process, and these are consistent with what we get from the 3D tracer. So that's quite encouraging. And of course, we want to extend this beyond the Milky Way and go to a cosmological volume where we can do this across the mass spectrum of thousands of galaxies. And this is indeed what we've started to work on. This is a little movie showing the evolution of a 34 megaparsec cubed cosmological region with the same physics that I just showed you, but resolving all the galaxies in this volume, where we have one galaxy cluster and about 3,000 galaxies and about 80 Milky Ways. So the statistics are going to be much better for the Milky Ways, and we're going to have the entire mass range of galaxies. And there's already a lot of results coming from this new simulation. And in particular, I would like to highlight this result by Marta Reina Campos, who some of you might know. She's been looking at the spatial profiles, the projected spatial profiles of the globular clusters and how they relate to the galaxy proper and the dark matter halo properties. And she finds that the half number radius of the globular cluster system is a good tracer of the dark matter halo structure. So it traces both the virial radius and the concentration of the NFW profile. So that's quite interesting that every globular cluster property that we seem to look at has some information on the assembly of the galaxies. And so now I'd like to leave our home galaxy and go out into the local universe and talk a bit about this exciting new class of ultra-diffuse galaxies and why they're so good at forming globular clusters. These galaxies have been cataloged since the 80s, but it wasn't until 2015 that observations with the specialized dragonfly instrument pointed at coma, as you can see in this image here, found 50 of these very, very diffuse fuzzy objects. You can barely see them against the background. These are more diffuse than 24 magnitudes per square arc second. And they seem to be everywhere. They seem to be in galaxy clusters, in galaxy groups, even in the field. And they seem to have the stellar mass of dwarf galaxies, around 10 to the 8 solar masses. And the concentration of their light, this is why I say sizes in quotes, the concentration of their light, the half-light radius is comparable to the Milky Way. And so they're very diffuse, but it turns out, as Nacho found out recently, that the break in the stellar profile is actually at the place where you expect dwarf galaxies to be. So it turns out that they're not failed Milky Ways, as some people thought. They're more likely to be dwarf galaxies that somehow got very diffuse. And this is going to be important later on, as you'll see, for understanding where they come from. Further studies found, as you can see in these images here, that they're covered in these little bright dots. So ultra-diffuse galaxies, at least in coma, seem to contain 7 times more globular clusters than normal galaxies of the same luminosity. You can also see that here on the right side, shown in terms of the specific frequency, the number of globulars per galaxy luminosity. So they're much better at making globulars than normal galaxies. And you might see why I think this is so puzzling. These galaxies are very diffuse. They're barely able to form any stars. Presumably very low star formation rate surface densities, and somehow they're able to form some of the densest stellar systems that we know, which we know require very high gas pressures and very extreme conditions. So this is quite paradoxical, and so this makes them quite interesting. And the situation got even more puzzling when these 2 galaxies in the 1052 group, DF2 and DF4, were studied in detail, and they look like pretty normal UDGs, except that they have each about 10 globular clusters or more, which seem to be at least 4 times more massive than in other galaxies. So in other galaxies, we find a nearly universal globular cluster mass function that peaks at around 2 times 10 to the 5 solar masses. These objects are consistent with the most massive globular clusters found in the Milky Way, up to 10 to the 7 solar masses, which is the larger than some galaxies. And so this became very controversial, mainly because the result changes a lot depending on the distance, and the distance was very difficult to measure. So there's been quite a heated debate about the distance. This is how such a dominant globular cluster population would look like on a normal dwarf spheroidal galaxy. So you see how important the globulars are in these galaxies. And it got even more interesting when Van Dokkum and his group measured the velocity dispersion of the stars and the globulars out to large radius, which allows you to set a very tight constraint on the halo mass. And they found that these galaxies are consistent with having 0 dark matter, or in other words, their dynamical mass to stellar mass ratio has to be less than 1, which for galaxy formation is a huge puzzle, because we assume that the scaffolding for forming galaxies is the depth of the potential well of dark matter halos. And without these, it would require a serious revision of the model. The last paper that in this debate came actually last week, when Celie Shen and collaborators used 40 orbits of HST to get the deepest observations of these galaxies, to get to the tip of the red giant branch, and precisely constrain the distance between DF2 and DF4, which is now 2 megaparsecs. And this tells you that at least one of these dark matter deficient galaxies has to be isolated, if not both, which makes this even more confusing, because all the models that have been put forward to date for how a galaxy can lose its dark matter have to do with tidal stripping in a high density environment. So if these things form in isolation, we really have to start over and think of intrinsic processes that can produce ultra-diffuse galaxies and ultra-diffuse galaxies without dark matter. And this is very, very difficult. And to add to the confusion, the same in this last year and the year before that, people went looking for in the alfalfa, which is an H1, a blind H1 survey, and they found these ultra-diffuse galaxies that are H1 rich. They have much more H1 than stars. They seem to be offset from the baryonic Tully-Fisher relation. They seem to be above it, which tells us that they have near or above the cosmological baryon fraction. But this is another way of saying that they're also dark matter deficient. Some of these objects, the kinematics are completely explained by the gas and the stars. So here we have H1 rich star-forming ultra-diffuse galaxies in the field, and we also have quenched ultra-diffuse galaxies in the field, both missing dark matter. So we need a model that can explain both. And so this prompted us to DF2 and DF4, and its weird globular cluster mass function prompted us to look at the initial cluster mass function and how it depends on galactic environment. And I don't have time to get into the details here, but you're welcome to ask me. We put together a model where the initial cluster mass function depends on the interplay between feedback and galactic dynamics, and this has an effect on the minimum mass of the sector mass function and the maximum mass. And the logarithmic slope is simply set by the hierarchical nature of molecular clouds. So just to give you an idea, this is the dependence of the minimum, the maximum cluster mass, and the width of the cluster mass function on galactic environment. You can focus on the gas surface density, which is on the x-axis, which is driving most of the variation, and going from the solar neighborhood to high redshift galaxies in the center of the Milky Way. And you can see that there's a large variation in the initial cluster mass function driven by the gas surface density and pressure. And because the maximum and the minimum vary differently, you get a non-monotonic variation of several orders of magnitude in the width of the cluster mass function. So we find that this can explain the weird cluster mass function in DF2 and DF4. Here's, for example, a comparison of the predictions for the Milky Way M31 and for the central molecular zone of the Milky Way, where the conditions are of very high gas density and very high shear. And you can see in that particular case, the mass function collapses into a very narrow peak. And so this is what might have happened in DF2 and DF4. As you can see here, we can take now the globular cluster mass function and find the conditions, do archaeology, and find the conditions that gave rise to these globular clusters. So this gives us a snapshot of the galaxy 10 gigayears ago. And this purple band is showing you what the initial cluster mass function was in that object. And that comes from very high gas surface densities, about 1,000 solar masses per parsec squared, and also very high shear, so very high volume densities of gas. So we conclude that DF2 had very extreme star-forming conditions of redshift higher than 1. And just to illustrate how extreme this is compared to now, this is the current constraints on the mass distribution of the galaxy. And this is what we get for the cold gas distribution. So the cold gas or the density must have dropped by more than a factor of 20. The galaxy expanded dramatically. Also, the absence of a nuclear cluster points to a major merger as the origin of this burst, but this still leaves the question of what caused the expansion of the galaxy. So this is the question that we were left with at the end of this study. So to conclude, we find that galactic environment shapes globular cluster populations, and that we can use this influence to understand the conditions in these objects at high redshift. And so the overabundance of massive clusters is the result of high gas pressure and shear at cosmic noon. And the existence of these globulars points to very compact UDG progenitors at high redshift that expanded dramatically. And so we're left with the questions: does feedback from globular clusters affect the evolution of galaxies, perhaps? Is there a connection between these two properties, diffuseness and the overabundance of globular clusters? And could also the globular cluster feedback have something to do with the lack of dark matter in some UDGs? So for that, we get to the last point that I want to make, which is about globular cluster feedback and galaxy formation. And for this, we went back to the drawing board, to the fundamental connection between galaxies and dark matter halos, which is sort of which is represented in the stellar mass halo mass relation that you see here. This is constrained currently from using cosmology, the lambda CDM model, and also surveys of galaxies statistically. So in halo abundance matching, you can get a constraint on the average relation, which is shown by the thick black line, and also its scatter, which is the gray band. As you can see, it's very small. And in the region where we run out of constraints, I marked that with a dashed line. And I'm also showing the cosmic baryon fraction, which gives you the budget of each galaxy, the baryon budget of each galaxy. So technically, you shouldn't be above this line. And also the line where the dark matter halo mass equals the stellar mass. But now let's look at the individual constraints from galaxy dynamics. This is a compendium of galaxies. The orange points are the spark sample, the blue and brown are nearby dwarf irregular and dwarf galaxies. Most of these are isolated and should not be heavily stripped, so their dark matter halos should not have lost a lot of mass. And you can see here already that the scatter seems to be a lot larger than predicted by halo abundance matching, up to almost the cosmic baryon fraction. And if I add here these pathological galaxies, some baryon-rich galaxies, and DF2 and DF4 as shown by the stars, and also these red pentagons, which are the gas-rich UDGs found by alfalfa with kinematic measurements, you can see that they're way above the median relation, and the scatter seems to actually increase above the cosmic baryon fraction to the point where you don't need dark matter to explain these objects. So this is just an extension of what's happening with normal galaxies. So you can think of UDGs in this sense, perhaps. And so in this model, we start with the premise that scatter in stellar mass at fixed halo mass correlates with the assembly timescale of galaxies. And this actually emerges naturally in simulations like Eagle and Illustrious, where at fixed halo mass, halos that collapsed earlier have larger stellar masses. And this is sort of understood naturally because they have more time to form stars and they have deeper potential wells, so they can convert more of their gas into stars. And I'll just walk you briefly to how we put together the model. We choose a halo mass and then the allowed scatter around the mean relation up to the cosmological baryon fraction for simplicity. And this gives us an allowed range of stellar mass. Then we assume that the scatter correlates with the halo concentration, so that earlier collapsing halos have larger stellar masses, like I just said before. And here you can see a synthesis of these. The dotted line is the cosmic baryon fraction, and you can see the cosmological trend of increasing concentration as you go to lower halo masses, but also as you go above the relation, this increase in concentration to the halo collapse redshift. So starting from this assumption, we can already predict, or we can model the populations, the stellar populations and cluster populations of galaxies at the redshift where their halo collapsed. And this is what we do here. We use the empirical relation between the virial radius and the effective radius to get an initial size at that redshift. And then together with the stellar mass, this gives us a fraction of stars that formed at that epoch, which we assume is 20%. This gives us the surface density of star formation. Using the Kennico-Schmidt relation, we can turn that into gas surface density. And because we know the sizes of the galaxies and we know the surface densities, we can fully specify the gas and the stellar profiles if we assume they're exponential. And we assume NFW for the dark matter, so we completely specify the mass profile. And so here I'm just showing you briefly what we get for the star formation rate, the initial radius, and the surface densities. And the main thing here is that as you go up from the mean stellar mass halo mass relation, the star formation rate goes higher because these galaxies have more stars and because they form them in a shorter amount of time. And this has a consequence on the surface density of star formation and on the gas surface density, which are much higher than for galaxies on the relation. So these galaxies are more compact. And these are exactly the conditions that you need to form massive star clusters. And so assuming hydrostatic equilibrium and the model that I described previously for star cluster formation, we can get the fraction of stars that form in clusters and the initial cluster mass function, and that fully specifies the cluster population, so we can get the number of globular clusters that are formed initially at that redshift. And so this is showing the bound fraction, and you can see that it increases by a factor of 10 from the mean relation to the maximum. So galaxies near the cosmic baryon fraction can form, at that redshift, can form all of their stars in bound clusters. And also the mean cluster mass increases by several orders of magnitude. So these clusters are going to be more massive also. So more stars in bound clusters and more massive clusters. And this is exactly what we need to explain the weird populations in UDGs. So we can then take the clustering of the supernova and the results of detailed simulations on the gas outflows from the galaxy and obtain the wind energy loading of the outflows. And you can see that it also increases by about a factor of 10 as you go from the mean relation to the cosmic baryon fraction. So these galaxies have more efficient galactic winds, and galactic winds coupled to the dark matter and heat it and expand it to create a core. So we can assume conservatively that 10% of this energy goes into the dark matter halo core size, and then use the core NFW model, which is based on simulations, to obtain the half-life radius of the stars and assume that the young stars are not expanded as a simple approximation. Then we combine the old and young star populations to get the distribution of stars and dark matter in the galaxy at redshift 0, and then we're done. So now I'm going to show you some of the interesting results that we got. We find that galaxies above the stellar mass halo mass relation from larger globular cluster populations. So here you can see, compared to constraints from nearby galaxies on the number of globular clusters, and we can recover the trend of increasing number of globular clusters as you move upwards from the mean relation, which is quite interesting because this is where UDGs seem to be sitting. And this is driven by more efficient wind driving. The more efficient wind driving by clustered feedback from the globulars heats the dark matter and the stellar orbits and expands the galaxy. These galaxies that have more globular clusters are also more expanded. As you can see here, this is now showing the core, the radius of the dark matter core, the effective radius of the galaxy, and the dynamical to stellar mass ratio within 8 kiloparsecs. And I'm highlighting the observed region where UDGs sit. And you can see that where the UDGs observationally are located, this is where we obtain the maximum effect. The larger dark matter cores, the larger effective radii, and the lower dynamical to stellar mass ratios. And there's a diversity of these ratios going from 1 to 100. So we get a diversity of UDGs, ones that are dark matter dominated and some that are missing dark matter. So this is quite interesting that such a simple model can give you all these results. And we also find that the expansion is mostly driven by the enhanced outflows from the overlapping of the supernova in the young clusters. And this is showing you the ratio of these quantities for the model with cluster feedback versus a model where you don't assume any effect from the clustering of supernova. And you can see that most of the effect on galaxy expansion is due to clustering of the supernova. And this is something that has typically not included in hydrodynamic simulations because modeling the clustering of stars is very difficult. It is included to some degree, but not like in this model. So we think that this is an important process to include. And so just to wrap it up, if we go back to the initial plot that I showed you on these pathological galaxies like DF2, DF4, and these other field UDGs that seem to have almost no dark matter, we can produce, using this model, specific detailed predictions for the mass profiles. And this is what I'm showing you here on the right. This is the dark matter mass enclosed within 8 kiloparsecs, and you can see that there's a region above which you transition into starting to lose a lot of dark matter. From the constraint on the stellar mass of DF2 and DF4, which is about 2 times 10 to the 8, we don't know the halo mass. Assuming that we don't know the halo mass, we can put a few models along this region to see what predictions we can make. And so for the model that sits on the stellar mass halo mass relation, this one right here, you can see the dark matter halo is just too massive. Feedback has some effect on carving a small core, well, actually not so small, but this is not nearly enough to fit the dynamical constraints at large, especially at large radius. As we move forward towards the cosmic baryon fraction, the halo mass is smaller because of this large scatter here. So we already start at a lower circular velocity, and the effect of feedback is much more enhanced, so we can carve the rest of the dark matter halo to get it into agreement with the constraints from observations. So this is quite encouraging. We also did the same thing for the predictions for the gas-rich UDGs. You can find these in the paper, you can ask me. And so to conclude, we find that galaxies that lie above the median stellar mass-halo mass relation formed earlier with higher gas and surface star formation surface densities. They also formed more globular clusters because these conditions were better for the formation of massive clusters, are much more effective at launching winds due to clustered feedback, and due to the clustered feedback evolve into UDGs driven by the expansion of the stars and the dark matter. And we find that the scatter plus the strong feedback from the young globular clusters can lead to a large diversity in the dynamical mass to light ratios. And galaxies near the cosmic baryon fraction can grow large enough cores and evacuate most of their dark matter, leading to galaxies with very low dark matter content and fitting the constraints that we have for some of these dark matter deficient UDGs without, and this is something that I like to stress, these galaxies are isolated. So all these processes are intrinsic and they fit the constraints for some of these galaxies that are also isolated. Thank you very much.
Well, thank you very much. Is there any question? So for people that have question, I will ask you to raise your hand. And yeah.
Should I start with the first? I don't know how to raise a hand in Zoom. I'm physically raising my hand. So thanks a lot for this very, very interesting talk. There is a lot to be taken out of it. I have a very general question, like how do you actually form and implement the physics of globular clustering in your simulations? Because that's what makes the whole novelty, let's say, of this simulation. So, for example, do you follow globular clusters through the dynamical frictions? Can you just tell us a little bit more about what are the subgrid models that you implement?
Definitely. So I actually have a slide for this. I was prepared. Yeah, thanks for that question. So yeah, I didn't have to get in time to get into this. This is quite a lot of years of a lot of work. And so the subgrid model, in every star particle, you have a population of clusters. And these clusters evolve on the fly based on the formation model and also the mass loss model. So the formation model comes from something similar to what I described, which is a model for the cluster formation efficiency, the amount of mass that goes into bound clusters. And this is what has been shown to reproduce local cluster populations. The Schechter cluster mass function that I also described. This one does not include the environmentally dependent minimum mass, which was something that came later. It's going to be in the next generation of simulations. But the maximum mass depends on the environment of the galaxy, on the surface density and the shear. And you have mass losses model using stellar evolution, including stellar evolution, tidal shocks, and evaporation, using the local tidal field of each cluster particle, which is relatively easy to measure in the simulation. This is the advantage of having a simulation versus an analytical model. And then we also include dynamical friction in a very simple way in post-processing, simply to estimate the fraction of clusters that would have spiraled into the nucleus of the galaxy by redshift 0, and then we take those out. This is for E-MOSAICS. Something that I didn't have time to mention, there are some shortcomings of the simulation. As you might know, Eagle is a very specific galaxy formation model. It does not have cold gas. This was what makes it so effective in modeling a large population of galaxies, modeling the subgrid physics the physics of gas cooling and star formation is one of the most difficult parts in simulations. And we're working on the next generation of simulations. The first result just came out. Actually, I was in a meeting today where we saw the cluster populations formed in a simulation using Arepo that includes gas cooling down to very low temperatures and new models for star formation and feedback. And we can reproduce the entire mass function of globular clusters and not just the high mass end. Before we had this problem because Eagle doesn't have cold gas, it cannot disrupt effectively it doesn't have molecular clouds, so you cannot disrupt, you don't have the tidal shocks from that cold gas. And now it seems to be working, and this is something that Marta Reina Campos has been working on a lot, and there's going to be results coming out soon.
Thank you. Jorge?
Okay, thank you. I have the first question and a comment. The question somehow is related to what Ariana asked. It's about the way in which you introduce the globular cluster, or you produce the globular clusters in the first simulation. So, but if I understood you correctly, you introduce them by microphysics, so by hand, basically.
Indeed, exactly.
Okay, so do you have any idea of how the mass function of these globular clusters compare with the globular cluster mass in the Milky Way?
Yeah, and so this is the holy grail of globular cluster formation models. This is the first thing that you try to reproduce. Unfortunately, I don't have the plot here, but I can point you. This was published in this paper here, Pfeffer et al. 2018, and also in Krausen 2019A. Or if you look in ADS for E-MOSAICS, you'll find it. This was in the paper that presents the simulations. They did a comparison with the globular cluster mass function of the Milky Way and M31, which are the two that we know the most. However, the Milky Way and M31 have slightly different, or actually very different, globular cluster mass functions, and this might be related to their particular assembly histories, as I tried this earlier. So you can only compare it statistically, but indeed the high mass end, so for clusters more massive than about 10 to the 5 solar masses, you reproduce that part. Below that, the mass function in E-MOSAICS in the simulation keeps going up. So you have actually more lower mass clusters than more massive clusters. There's no peak. And this problem, as I was just saying, has to do with the fact that there is no cold gas in the Eagle model. So you don't have enough tidal shocks to disrupt these clusters efficiently. And so we've been developing the next generation of simulations for the last 3 years, trying to work out all the details of how to implement more galaxy physics at the same time as putting in the cluster physics. This was a lot of work and very difficult, but for the first time today, I saw a plot of the mass function actually, and it has the turnover, and it is consistent with what you see in the Milky Way. And this is because you have the tidal shocks in the cold gas.
Okay, and now the comment. And the comment is about the second part of the talk. So specifically about these gas-rich UDGs that seems to, some people present very low dark matter content. Mm-hmm. Now, I wouldn't bet a lot of money on this result, really, because in order to get the dynamical masses from which you infer the total mass and so the dark matter content, mm-hmm. once you have the stellar mass, you have to correct for the inclination of the galaxies. Mm-hmm. Okay, now this is done assuming that they are disks, and dwarfs are not. So they have triaxial shapes. Now, if you kind of make a toy model of what the effect of the triaxiality could be, then you get a lot of fake dramatic poor objects, very, very similar to what is detected. I have a paper on that that was published a couple of years ago.
Yeah, very interesting.
I wouldn't put a lot of money on this result.
Yeah, thanks for that. Yeah. I've been really trying to follow this this community of dynamical models. Yeah, I don't do these myself, but from reading the work by Filippo Fraternali's group, I got the impression that they find that these objects in particular have very nicely behaved cold gas disks, H1 disks, and that it's very difficult to get the inclination. But
they are dwarf galaxies, so they cannot have very nice, well-defined disks.
Well, but in the gas, right? It's different in the gas versus the stars are a mess, but the gas, I think they claim that the gas is very cold and well behaved dynamically. So this is why this is why I think they say.
Okay, so that was my comment. So thank you.
Thank you.
I have a question. Hello, I have a question.
I guess.
Sorry, Kame. Yes, sorry, my mic was blocked. Kame, please.
Okay, thank you. I'm Dena Prieto. Nice to meet you, and thanks for your talk.
Nice to meet you.
Yes, you have perhaps focused in the Milky Way and Andromeda with the globular clusters. We have systems like MT7, Perseus, where the number of globular clusters are in the thousands.
Yeah.
10,000, 15,000. So we know very well how this, we know very well. We know because of just statistics, how is the population of the globular clusters distributed in the galaxy. Yeah. These are very old systems. By definition, globular clusters are among the oldest systems in galaxies or in the universe. So if I go to MT7, but the same could be in Coma or in others, the globular clusters divide, you might know very well, in the red and blue population, white metal and very low metal, the blue one, the red one, high metal clusters. And the red population follow very nice the light distribution of MT7 or in Perseus or in Coma, up to the very central parsecs. So obviously, while the block population is not the case, it follows a distribution, but not really in line with the galaxy. Obviously, the fact of the red population alone tells us how these clusters are formed in line with the stellar light as well, because otherwise it won't be possible that they follow to each other such a almost perfection. It's almost magic when you see that.
Yeah.
So I think it would be nice, I mean, in your modeling to constatate with this type of observations. And my point was always, is very intriguing for me. If globular clusters, as they are and are dated, are very old systems, and of the ages of the stellar population in a galaxy like MT7, which is a very old guy, might be related with the epoch of formation originally for mini dark matter halos, for example, in the big halos in which perhaps MT7 would have formed. And so I just, perhaps this is a little bit controversial what I'm saying, but it could be fit or check, or what is your opinion? I mean, these globular clusters had to form very close in time with the stellar light of such an old system. So it could not be by mergers. Okay. This is a phase that happened after. So the population is also already set up following the light distribution of the stars to the center. So they are subjected to the potential very well. and you follow that over kiloparsecs distance across the bulge of the galaxy, in Perseus, in Coma, etc., where we have such a huge statistic on the thousands, tens of thousands. So would be a way perhaps that to check, since you are introducing the globular cluster population, something which is not usual in cosmology modeling.
Well, this is the thing, that we're trying an approach that we think is a bit simpler, because we don't have to, I personally, I like it because we don't have to assume any exotic physics like formation of globular clusters in dark matter mini halos. This is simply a consequence of galaxy formation, but
Yes.
and because you need high pressures to form globular clusters, it's almost automatic that they form at high redshift, right? The thing is that galaxies of different masses form at different rates. You know, in the downsizing phenomenon, Milky Way mass galaxies do not form their stars at the same rate as M87. M87 is mostly old, and it's quenched, so it stopped forming stars. This difference is when you compare so when you compare the stellar component to the globulars, are going to give you quite a different picture, I think, when you look at the Milky Way. And for example, today we were looking at the formation histories of the globulars in this volume that I'm showing here as a function of mass compared to the Madao diagram, for example. Even though galaxies seem to know which mass halo they form in, the globulars all seem to prefer to form early because the conditions are better at early times. So perhaps, we have not checked this because we're just starting to work on this simulation. Perhaps you can look at that cluster. We have a galaxy cluster. It's not as massive as Coma, but we could look at very easily at these correlations between the stellar light and the populations of globular clusters. And this is a very interesting thing to understand where it comes from. The fact that the red clusters trace the stellar light.
Nothing known since many years, but I would say that in our Milky Way we have globular clusters that are very old, comparable to the age of the universe.
Yeah, the issue here is that the uncertainty in the ages is large enough that you could say, I guess you could say that a lot of them formed at redshift greater than maybe 3. And 3 just happens to be where the formation history of the cosmic star formation history peaks, and where the conditions are ripe for forming globulars. So unfortunately, until ages are more precise, we cannot really determine if the clusters formed before the stars. I think this is my understanding of this. It's mostly an observational problem, but that we reproduce a lot of the observables of globular clusters in the simulations without the need to form them via mini halos or collisions of galaxies or other mechanisms that have been invoked in the literature in the last years. So it's kind of a simple explanation, and this is why I like it.
Okay, well, thank you very much. So for the last 2 quick questions, Nacho and then Kami. So Nacho first.
Okay. It would be quick because I don't have too much time, but it could be, I would be talking for a lot of time. Yeah, so I think that you have not shown all the evidence against, for example, that these galaxies that you are mentioning, Dragonfly 2, Dragonfly 4, are really far away. So you have just focused on some group data, but not the rest of the evidence as well. And as you know, it's absolutely key to have all the evidence before, you know, embarking yourself in such a, you know, in a theoretical analysis of the data. But anyway, having said that, for example, in the case of these galaxies, it's not only that they have a low amount of dark matter, but also the properties of the globular clusters if you put it far away, are weird. And normally people just concentrate on their brightness, but it's also their sizes.
Yeah.
Okay.
Yeah.
So whatever mechanism, I mean, there is kind of, you need to understand that if you use a regular model for forming globular clusters, you could not form these globular clusters if they are far away. I mean, they have to form in a completely different way unless you know how they should be like 4 or 5 times larger and also brighter than regular globular clusters. So a mechanism that form normal globular cluster cannot form this cluster. This is what I mean. Because the globular clusters these galaxies have, if they are far away, are like Omega Centauri, for example, that we think it's the center of another galaxy that is now disrupted. So they are not normal. However, if these galaxies are closer, as many evidence suggest, including the tip of the red giant branch of this deep data that has been just released, and so you have to wait for our analysis. Then everything is normal. The size of the globular cluster, their brightness, and the typical amount of thermal. So this is a common. But coming also in terms of the diffuse galaxies, ultra-diffuse galaxies are they only show an excess in the number of globular clusters if you use the specific frequency. And the specific frequency, if you can show an example of a figure with a specific frequency, yes, the specific frequencies have two axes: the number of globular clusters and also the brightness of the galaxy. And the brightness in a wavelength, which is the B band. Okay, so as you can see, that globular clusters that are so if you look at which galaxies would have the equivalent number of globular clusters, are those that have of the order of 1.5 to magnitudes brighter in the B band. Okay. So these galaxies are regular dwarf galaxies forming stars. So if you just stop the star formation of these galaxies with B band, let's say -16, they would become fainter, and then you would have the number of globular clusters similar to what you see in ultra-diffuse galaxies. So in short, so if ultra-diffuse galaxies could be either special because they have a large number of globular clusters, or could be special simply because they are dwarf galaxies without forming stars at the moment, or they stop forming the star some time ago. No, so it's up to you to decide in which sense the evolution was. But when you make the same plot, but instead of using the absolute luminosity, you use the stellar mass of the object. The objects are normal. So.
Oh, okay.
So they are not special in this sense.
Is this true? Is this true in general for many UDGs?
For the vast majority, you can check Morisco 2017, where he did the exercise with many dozens of ultra-diffuse galaxies, but instead of using absolute magnitude, the stellar mass. Anyway, okay. I talk to you later, and then we can go.
Yeah, very interesting. Thanks.
No problem.
Okay, thank you. So I think that we can stop here. So we can thank Sebastian again, and see you on Thursday for a talk from a camera.
Sorry, Guillaume, I think there was another question.
Oh,
Carmen's got her hand raised in
but
an hour.
Yeah. Okay.
Yes, my hand was raised first than any other hand.
Any other one?
Oh, sorry. Yeah, unfortunately, we cannot see that with Zoom.
Okay, I have a very quick question, I think, and well, thank you for the talk. I really enjoyed it. And my question was about the first part of the talk regarding the formation of the Milky Way. And in particular, you say that the main progenitor would have formed half of the mass around 8.7 gigayears ago. In the case of the main progenitor, I guess we should look for this mass in the disk, basically. I'm asking this because we are working on producing star formation histories for the Milky Way, and this is what I'm going to talk in Thursday, in fact. And it turns out that in a star formation history that we have for a volume of 2 kiloparsecs radius around the sun, we have basically precisely this number. It must be by chance, of course, because
I'm very happy to hear this.
we did say that we did think that this volume could be quite representative once you take into account the migration azimuthal movements and also the radial migration. But I wanted to ask you this. I mean, if we wanted to check this observationally, in the case of the main progenitor, we should be looking at the disk, basically, right?
Yeah.
At the mass
and kinematically separate or take out the halo and the thick disk, I guess. Or this is where it gets very complicated, I guess, no?
But not the thick disk. I mean, the thick disk is part of the disk. I mean,
yeah, I guess, but I don't know what the consensus is. But some people say that it's accreted. Some people say it's in situ. I don't know.
Well, no.
But I guess you know. I think you know better.
The thick disk needs to be in situ. I mean, both the thin disk and the thick disk must be in situ. And then some of the halo we claim is in situ as well. In the sense that it has been just scattered from the
yeah.
Okay. Well, yeah, it was just.
No, but that's good to hear. Well, actually, that's why we separated the main progenitor from the total thing, which is right above the stellar mass. If you don't care where it formed, that one formed even earlier, because a lot of a small fraction of that came from progenitors that formed earlier. So that biases your estimate towards older ages. But yeah, that's
those would be mostly in the halo. I mean, the accreted progenitors.
By fraction, although the Gaia sausage, kinematically, the Gaia sausage is in the Milky Way, but kinematically it's still distinct, I guess. Yeah.
Okay, thank you.
Thanks.
Well, so thank you very much all for attending to the talk, and thank you again, Sebastian, for this really nice seminar.
Thank you for having me.
So have a good day all, and see you on Thursday. Bye.
Bye.
Bye, Sebastian. Bye-bye.